introduce for you chapter 32. And for chapter 32, I hope I will be able to finish it in only like 2 lectures. It's very short, and let's start. Now, today we will talk and introduce electromagnetic waves, and we are going to talk about general physics of electromagnetic waves and how to connect with Faraday's law and Beer's law, Maxwell's equation. Therefore, the first thing we are going to understand today, how electromagnetic waves are generated. What's like the process of generating these? How and why the speed of light is related to the fundamental constants of electricity and magnetism. We're going to see that we will be able to evaluate or find C, which is the speed of light in vacuum, using using epsilon zero and mu zero, or like epsilon and mu. How to describe the propagation of a sinusoidal electromagnetic wave, a wave that is really, again, the wave may like, let's go back to the definition. It's a disturbance that is gonna, oscillate in space and time. And then we're gonna see the dependence of the wave on like space and also time. What determines the amount of energy and momentum carried by the electromagnetic wave, and how to describe the standing waves, electromagnetic waves, and how really they are really related to applications in our life. Now, why do metals reflect light? And like we are going to go and look at how really is really the interaction of electromagnetic waves, which we will say light is part of it. We will see that light, it is an electromagnetic wave. And when we say light, we will maybe most of the time referring to that just narrow band, which is just in the visible light. There are many other examples of electromagnetic waves, and they are really extending from radio waves, microwaves, X-ray, gamma ray, UV, ultraviolet, infrared. Unlike sound or waves on a string, these waves do not require a medium to travel. When we introduced the waves before in Physics 201, we said that these waves, usually are I would say, divided into two categories. One of them is mechanical, and the other one is non-mechanical. The mechanical, like sound waves, they need a medium, and we talk about non-mechanical like light, it doesn't need a medium. One of the most famous names in this field is Maxwell, James Maxwell. And, this physicist was working with, electromagnetic waves, was the first person to truly understand the fundamental nature of light. And he proved in 1865 that an electromagnetic disturbance should propagate in free space with speed equals to that of light, the one that we call it speed of light. From this also he was able to conclude and deduce that light was an electromagnetic wave. According to Maxwell equations, we have an accelerating electric is gonna produce electromagnetic waves. Then just simply, if I have an electron that is oscillating, that is accelerating, it can produce electromagnetic waves. And for example, here in this picture, you have power lines, the high power lines. They carry a strong alternating current, which means that a substantial amount of charge is really accelerating back and forth. And if you will go nearby, your car will, the radio will produce a buzzing sound because the car radio was able to, to receive these. Now, also here, we can say that there is a spectrum called electromagnetic spectrum, and that electromagnetic spectrum extend from, I will say, frequencies or wavelength. We can say from radio waves, moving to microwaves, to infrared, to the visible light, ultraviolet, and ultraviolet, and then X-rays, and then gamma rays. And it's a wide range of frequencies and wavelengths, and therefore we're gonna find that it is here like a log scale, because it's like it's a very I would say long range. Now, it's very important for you to understand that, waves that they are really very long, or they have long wavelength, they're gonna have short frequencies. And therefore, when we talk about radio waves, these waves are really the ones that they are sitting here. These are really very long in wavelength. Then it's like the range of like 10. Whereas when we talk about the frequency, they are in the frequency range of 10 to the 8, whereas on the other, I will say extreme, we are going to have very short waves that they are really the gamma ray, which are really also, having very high frequency. And something also we need to know that the frequency is, it has to do with energy, and therefore I will say the when we talk about the gamma rays, they are very dangerous because they are high frequency, high energy. Now, you can see here this narrow band here. It is the visible light, where we have red, orange, yellow, green, blue, and violet. Or, these now, the spectrum, you used to know that they are 7 colors. They are now set to 6 colors. They excluded indigo. And I will say here, when we're going to talk about some of the problems, they might ask you in which range is this. Then you need to know there is a table here that you need to know what is really the range for each. Like, we don't have these strict boundaries, but it's an average thing. Then the visible light is the segment of the electromagnetic spectrum, the only segment that we can see. And visible light extends from 400 nanometer, which is the violet, to the red, which is 700 nanometer. But like also these approximate boundaries for different colors. Now, this is really very interesting. It is ultraviolet vision, and here you're going to see that we are talking about insects and birds. They can see ultraviolet waves that humans cannot. Then for us, this is what we are going to see from these Susans, black-eyed Susans. Whereas this is what the picture is gonna appear to birds and insects. Some of them is gonna be a UV. For us, of course, this was taken using a UV sensitive camera, but it's really very important for birds and insects, and they can clearly see what is the central spot here, because this is very important for them. For bees, for example, for when they use these to pollinate. Now, also here, we are going to derive some equations, and I will say, to begin our study of electromagnetic waves, we imagine that all the space has all these divided into two regions by the plane that is perpendicular to the x-axis. And this is really here. I will say the plane is perpendicular to the x-axis, and it is divided into regions. And this region here, we're going to have uniform electric and magnetic fields are shown here. And here the E and B are really zero. This is, we call it a wave front, and it is moving along the x-axis. We're gonna see like the two vectors E and E, they are perpendicular to each other, and they are perpendicular to the direction of the propagation, or like the motion of the wave. And because we're gonna talk about the again the right hand rule. Also, we can use Gauss's law and Gaussian surface to verify that in order to satisfy Maxwell's first and second equations, the electric and magnetic fields must be perpendicular to each other, which prove that the light wave, they are transverse waves. A transverse wave means that the oscillation of the oscillation is perpendicular to the propagation direction. Here, we are going to relate Faraday's law and Ampere's law. And, the derivation for me, it's not very important, but it's showing you here that we have here the electric field for an electromagnetic wave, and we have the magnetic field is going out of the page, and the vector dA is going out of the page as well. And then we were able to use the relation that is saying about the flux of the magnetic field and relating that to the electric field. And then we concluded from that that E equals C times B. Then for electromagnetic waves in vacuum, electric field magnitude should equal C, which is speed of light, which is the 3.0010 to the 8 meters per second, times B, which is the magnetic field magnitude. Ampere's law is gonna also relate here. It's the same, I will say, derivation, but it's gonna talk about the flux of the electric field, and it is relating here again the magnetic field and the electric field for electromagnetic waves in vacuum. Is talking about that B equals mu zero times epsilon zero times C times E. And this is again another relation that we can use also. Now, properties of electromagnetic waves, Maxwell equations imply that in electromagnetic waves, both the electric and magnetic field are perpendicular to the direction of propagation. As I said, we take usually B to be along the Z, and E, it is along the Y direction, the positive direction, and then X is the propagation. Also, in an electromagnetic wave, there is a definite ratio between the magnitudes of the electric field and the magnetic field. They are related by C. And also, unlike unlike the mechanical waves like sound waves, electromagnetic waves require no medium, and they travel in vacuum with that certain velocity, which is C equals 1 over square root of epsilon 0 mu 0. And if we put here the numerical values for this constant, we will be able to obtain that C equals 310 to the 8 meters per second. It's not 108, of course. Now, this is here just a diagram to show you the direction of propagation of an electromagnetic wave is the direction that is created by using the right-hand rule. This is E, this is B. E cross B, it's a vector that is along the x-axis, and this is the propagation vector. And here, because C, it is the vector C, it is the speed, the velocity of light. And here we have right-hand rule for an electromagnetic wave. If we point the thumb of our right hand in the wave's direction of propagation, we are imagining that E, it is rotating in the the fingers, they're gonna curl in the direction of B. Now, electromagnetic waves also produced, we said, by an oscillating point charge. They have sinusoidal waves that they are not actually plane wave, but we can, approximate that situation if we will go to a small region in space. Here we have, this is the oscillating electric field, which is the pink one, and this one, the blue, it is the magnetic field, and they are really the waves are really traveling in the positive x direction, the same as E to the B. And then we have, the Y components, they're going to be the electric field, and the X component, the Z components, they are going to be the magnetic field. Here we are showing also another wave that is polarized sinusoidal electromagnetic wave, and it is propagating in the negative x direction. And we can see that E and B also, they are really B here is along the negative Z, and E it is along the positive Y, and E cross B is going to be the direction for propagation. Now, we can describe the electromagnetic waves by means of wave functions, and these are depending on x and y and x and t. Then E as a function of x and t, it is j because it's along the y direction, E maximum times cosine kx minus omega t, and B as magnetic field, it's also depending on x and t, and k is the vector along the positive z, the unit vector, and B maximum times cosine kx minus omega t. I will say here, of course, E, electric field, and B, it is magnetic field. Omega is the angular frequency, and K is the wave number. And the wave travels to the light with the speed of light, that is c, that equals omega divided by k, which is the wave number. Also here, the same equation that we did introduce before, E maximum equals C times B maximum. Also now, let's assume here that the electromagnetic wave, it's not traveling in vacuum, it is traveling in any type of matter like air, water, glass, or whatever. Then now the electromagnetic wave can, the velocity is going to be different, and V equals 1 over square root of E times mu. They don't have the zero. And we can conclude here that is going to be C divided by square root of K. And K, it is the dielectric constant in electricity, and Km, it is the magnetic relative permeability from the magnetism. The ratio of the speed of C in vacuum to the speed of V in a material, it is known the index of refraction, and that index of refraction, it is showing us like how much really the wave, it is deflected when it enters the medium. C over V equals N, which is the index of refraction, which is the square root of K times Km. Also, we want to talk about the energy in electromagnetic waves, and here we will say that it is like any wave, it transports energy from one region to another. And there is a scientist, his name is Boyanting, was introducing a vector called S, and that is measuring the magnitude of that Poynting vector it is the power per unit area. Then it's power divided by area in the wave, and it is pointing in the same direction as the propagation, like the movement of the wave. And S equals 1 over mu 0 E cross B. Also here, we can say that the magnitude of the average value of S, it is called the intensity, and the unit for the intensity, watts per square meter. And here we are presenting for you many equations. We will solve one of the questions about intensity and how we're gonna use different expressions to calculate it. Then it is the magnitude of the average point in vector is going to equal I, the intensity. If we multiply E maximum times B maximum divided by 2 mu 0 is going to give you also the intensity. E maximum squared divided by 2 mu 0 C also, it is giving you the intensity. And finally, this equation 1/2 epsilon 0 C E maximum squared is going to give you also, we can calculate the I divide A equals power divided by the area. We're going to see in this in one questions. Electromagnetic waves also carry momentum, and therefore they can exert what is called radiation pressure on surfaces, and P radiation, or like the, I would say the momentum or the pressure, we call it the radiation pressure. It is S average divided by C and equals I over C. And if we have, this is when the wave is totally absorbed, when it is totally reflected, that radiation pressure is going to be 2I over C. Um, Also, we can have standing waves from electromagnetic waves, and they are really can be created by reflecting by a conductor or dielectric, and then they're gonna form what is called standing waves. And as the time elapses, the pattern does not move along the x-axis. Instead, at every point, the electric and magnetic field vectors simply they are really oscillating, and they are forming um, kind of nodes and antinodes. One example on standing waves in a cavity is the microwaves, and typical microwaves, they are using wavelength that is 12.2 centimeters, that is strongly absorbed by H2O molecules in food. And because the wave has nodes that they are really spaced as at W over 2, which is 6.1 centimeters, then the food should be rotated while cooking. Otherwise, it's going to stay cold. Okay, this is for the material, and then I will introduce the problem solving in another video.